Here, for a combination, the order does not matter. So everything we've done till now have been permutations where we have been arranging objects in a specific order. Well, what does it mean when the order doesn't matter? Well, when the order doesn't matter, and this is on page 722, when the order doesn't matter, it's talking about taking a selection of objects from a larger group. So here we say, how many ways can you choose 3 books from 4 books? And if we think about permutations in each of these, well, permutations, the order would matter. So you could have book 1, book 2, book 3, book 3, book 2, book 1, book 3, book 2, book 2, book 1, book 3, book 2, book 3, book 1, book 3, book 1, book 2, book 3, book 2, book 1. Whew. Those would all be different if you were arranging them on your shelf. But if you were just, you won a prize, and the prize is you get to keep 3 books and there's 4 to choose from. It's like, oh, should I choose book 1, 2, or 3, or 3, 1, and 2? Well, those are the same. You have the same books. You're taking the same books home. So the order doesn't matter. So we realize that all 6 of these are just 1, picking 1, 2, and 3. All 6 of these ones are just 1. All 6 of these are 1, and all 6 of those are 1. And so we have something similar to identical objects. When we have a combination, we would say all of these permutations are identical. And so we have to divide out the identical objects. And the way that we think about it is we are dividing out the order. So how do we go from 24 permutations, because we know how to count that, 3 spaces, 4 choices, 3 choices, 2 choices, for 24 in total, how do we get rid of the order? Well, we basically say, if I'm choosing 3 things, how many orders are there for each set of 3? Notice that there's 6 for each of these, which is equal to 3 factorial. So with combinations, you would say, well, if I had 3 items can be arranged in 3 factorial ways. That's my identical objects. That's my repetition. So I need to take my number of permutations and divide them by 3 factorial. So if we had 10 different chocolate bars, ooh, this sounds like a yummy question. And you win, and if you win, you get to take 7 of them home. The teacher still eats 3. That's just, can't give away all the chocolate bars. So there's 10 chocolate bars, and you win 7 of them. Well, if the order mattered, you would say, I have 10 choices for my first one, then 9, then 8, then 7, then 6, then 5, then 4. That's if the order mattered. But when you get the 10 chocolate bars, it doesn't matter which order you pick them. You still get to keep them. How many repetitions would we have to divide by? Well, since there's 7 items, we would divide by 7 factorial, because there would be 7 factorial arrangements that would all be identical. So this leads to the combinations formula. All the combinations formula is the permutations formula divided by how many objects you're choosing factorial, because that would get rid of the order. Now, if our combinations formula, or our permutations formula, is n factorial over n minus r factorial, then our combinations formula is n factorial over n minus r factorial. And there it is in that box. We write this all the time. In some university courses, in some IB courses, they'll use that notation, and we say N choose R. For permutations, we very rarely use the formula because spaces were easier. In combinations, we're going to use the formula all the time because the formula is really easy to use. So let's look at an example of how this would work. We've got a lottery. There's 80 numbers, and you choose 20. How many combinations of 20 numbers are possible? So as soon as you realize it's a combinations question, where either, in other words, this one says how many combinations, pretty obvious that it's a combinations question, but the main thing you're going to have to ask yourself is, does the order matter? Because I'm going to read a question. If the order doesn't matter, it's a combinations question. If the order does matter, then I'm going to have to use one of my strategies for permutations. So here it says how many combinations, and we're going to use the formula. 80 choose 20. And if you plug things into your formula, you're going to notice a neat pattern. Whoops. On the top is always the 80, just like it was with permutations. On the bottom, though, you will always have two numbers on the bottom. One of them is going to be the number that you see there, 20 factorial, and the other one is whatever adds up to 80. Whatever adds up to the top number. So the bottom two numbers, 20 and 60 in this case, will always add up to the top number, which is 80 in this case. And you have this button on your calculator as well. See if you can type it in to get 3.54 times 10 to the 18. The most famous lottery in Canada over the last, I don't know how many years, is probably Lotto 649. Have you ever, I think they write it like this, have you ever seen advertisements for that driving down the road saying that prize is now like 35 million, 40 million? How it works is there's 49 numbers, and they used to televise it. They used to have these balls bouncing around, and then one ball would come out, and that would be the first one, and then the second one. Now, what you have to do in Lotto 649 is, of the 49 numbers, you just have to choose 6 of them. And the order doesn't matter. If your 6 numbers get chosen, then you win the grand prize. So to figure out how many combinations there are, it's just a matter of 49 choose 6. $13 million, someone have it, 900,000. 83960 or something like that? 816. Seems odd. Okay. So 49 choose 6. There are almost 14 million different possibilities. But that's all the possibilities. So your chances of winning if you buy one ticket are 1 in 14 million. How likely is that? Well, if you take out a coin, okay, and flip it and see what do you get, heads or tails. I got tails. I need to get tails another 22 times in a row to be the same odds as winning the lottery. Do you think I'm going to do it? 2 times in a row? I'm going to buy a lottery ticket. Oh, failed. No. But you would have to get either heads or tails 22, 23 times in a row to be roughly equivalent to this. If you want, you can go home and practice flipping coins. It could take you up to 14 million tries before you get 22 in a row. But the idea is if 14 million people are playing, well, there's a better chance that someone's going to win because that many tickets out there. But some people will choose the same number. So even if 14 million people play, you're not guaranteed that all the numbers have been purchased. But if you want to win the lottery, if that's like on your bucket list, you can do it. You just have to buy every single ticket. Okay? So right now, how much are tickets? I think they're like, are they $2 or are they already up to more than that? I don't know. I don't play the lottery because I've done the math and I know I'm not going to win. So, right? But I think it might be $2 a ticket. So for a mere $28 million, you can guarantee that you're going to win the lottery. Okay? So next time it's at 40 million, just go to the bank and say, would you mind lending me $28 million? I'd like to win the lottery. Which could be good, right? It would be super smart if you were guaranteed to win the 40 million and you only had to pay 28 million. That seems like a pretty good deal. What could possibly be the problem? Your bank's not going to, well, yeah, the bank's going to look at you and go, no, you're not going to lend you 28 million to win the lottery. But what's the other problem? Well, there might be taxes. I don't know if there's taxes on Canadian lottery or not. I know the US, I think there is. What happens if someone else wins? Yeah, it's split. So it's 40 million. You just borrowed $28 million and someone else wins. So you win 20 million. The bank comes to your door with their big bats, like they come when they want their money. And you're like, oh, well, I won, but I had to share it. So it's $3 now. So you don't, it's around 42 million to win the lottery. Man, it's getting expensive to win the lottery these days. So yeah, 40 million, don't buy it. But if it gets up to 60 million, $42 million. But the problem is when it gets up to 60 million, more people buy. And when more people buy, then all of a sudden, you have a better chance of more people winning. Now, if you are paying $3 and you are expecting to win the lottery, I would say don't. It's not worth it. You're going to lose your money. However, when you buy a $3 ticket for the lottery, and if that $3 ticket lets you have the greatest imagination possible, like you imagine, oh, what would it be like if I won that money? And you think about all the amazing things you could do. If that fantasy is worth $3 for you, then it's totally worth it, right? At the end, you're not going to win. But if you really enjoyed thinking about all of those things that you could have if you won, then that $3 is worth it. So, questions for practice are 4, 5, and 7. Uh-oh, that doesn't look good. So we don't have a video for this one. Or maybe we do. In England, they used to have Lotto 649, but they recently, apparently I heard, they recently changed it to Lotto 659. So now there's 10 more numbers, and your chances of winning are even less than they were before. However, now, if you get 2 of the numbers right, you win a free ticket. So they say, based on the fantasy model of if that $3 helps you fantasize about winning, the Lotto 659 is even better because the prize money is even larger, but you're not going to win. But you have a good chance of winning an extra free ticket which allows you to fantasize even longer, so you get an even better bang for your buck that way, as far as you still lose your money in the end, but right? But somebody always seems to win. So there is someone who gets lucky and wins the lottery.